You know that gray sludge you always see at construction sites? Well, it might just look like simple muck, but it's actually a super high-tech liquid rock. Today, we're going to dive into the fascinating science behind how wet concrete works. A science that, believe it or not, decides if our biggest, craziest buildings stand tall or, well, you know.
So, on pretty much every single job site, anywhere in the world, you are going to see somebody doing this exact test. It's called the Slump test. For decades, it's been the one and only way to check if a batch of concrete is ready to go. But as our buildings get taller and our designs get wilder, you got to ask, is this old-school test really good enough to hold it all together?
So here's the thing. The slump test is, it's genius in its simplicity. You just fill a cone with concrete, pop it off, and measure how far the stuff slumps down. That's it. It gives you one number for what engineers call consistency, but that is literally all it tells you. It's completely silent on how that concrete is actually going to behave when you're, say, pumping it hundreds of meters straight up or trying to get it to flow into some wild curvy shape.
In fact, right there is the heart of the problem. For the kind of mind-blowing stuff we're building today, we've got to understand concrete on a way deeper level. We need to get way more scientific about how it flows.
Okay, check this out. Picture two different concrete mixes. One's got more fine sand, the other's got more chunky rock. Now, you can totally tweak them so they have the exact same slump value. But here's the catch. Try to pump them. The sandy one flows like a dream. The rocky one, it can jam up the whole operation. Same slump, but a totally different and potentially catastrophic performance. The test just didn't see it coming.
All right, so if the slump test is missing a huge piece of the puzzle, what's the answer? Well, it turns out there's a whole field of science that's all about how materials like concrete actually move.
And that science is called rheology. I know, it's a bit of a mouthful, but the idea is actually pretty straightforward. It's the study of how things flow. And for a concrete engineer, rheology is like a superpower. It lets them go way beyond this fuzzy idea of workability and instead gives them two super precise dials to control the flow of concrete with amazing accuracy. So what are these two magic dials? Well, think of them as the two secret ingredients, the keys that unlock concrete's true potential and let us design the absolute perfect mix for any job imaginable. Okay, and this breaks it down perfectly. On one side, you've got shear yield stress. Just think of this as the get-going force. It's that little bit of oomph you need just to get the concrete to start flowing in the first place. You know, like when you have to give a ketchup bottle a good smack to get anything out. That smack, that's the yield stress. Then you have plastic viscosity, and that's the keep-going resistance. So once it's already moving, how hard is it to keep it flowing? Is it like water, or is it thick and goopy like honey? That's viscosity. Simple, right? And boom, here's where it all connects. That old slump test? It's really just a rough ballpark guess at that get-going force, the shear yield stress. It tells us how much of a push it needs to start moving, but it completely, totally ignores the other half of the story, the plastic viscosity, how it flows after you get it going. And that's the crucial detail we were missing all along. So, how do you use this in the real world? Well, once you can control these two things, you're not just guessing anymore. You are actually designing concrete for literally any situation you can dream up.
Let's look at this like a control panel. Need a stiff mix for a basic foundation? Easy. You dial up a high yield stress so it holds its shape, but a low viscosity so it'll still move around when you vibrate it. What about a super thin wall that needs something really flowable? You want low yield stress and low viscosity, so it just pours in like water. And for the really cool stuff, like concrete that has to fill a packed space without falling apart, you want a low yield stress so it flows on its own, but a high viscosity so it moves together like a thick, cohesive river of honey.
This level of control is a total game changer. It's what lets engineers give concrete actual superpowers and create mixes that can do things that were once flat out impossible. So let's take a look at what these superpowers really make possible. We're talking everything from the tallest skyscrapers on the planet to concrete that literally acts more like a liquid than a solid. 600, what's that number? That's how many meters straight up they had to pump concrete to build the Burj Khalifa in Dubai, a world record. It's a feat that was only possible because the engineers were absolute masters of rheology. They dialed in the yield stress and the viscosity so perfectly that the concrete could make that incredible journey without ever failing.
This mastery has created some truly mind-bending materials. Take self-compacting concrete, or SCC. This stuff is the pinnacle of rheological design. It's a concrete engineered so perfectly that it flows like a liquid. It fills the most complicated shapes and weaves through tangles of steel rebar all by itself. No vibration needed. None.
So, what's the secret recipe for this stuff? It's just a perfect dance between our two secret ingredients. First, you design for an incredibly low yield stress, so low that it just starts flowing under its own weight. No pushing, no shaking. And second, you give it a high plastic viscosity. This makes the whole mix really sticky and cohesive, so as it flows, it doesn't separate. The water, the sand, the rocks, everything moves together like one single uniform liquid.
So the big takeaway here is that this isn't just some abstract science experiment. Understanding rheology is what lets us build faster and more efficiently. It's what lets us build stronger and more durable buildings. And it's what lets architects dream up these incredible, breathtaking shapes that, honestly, a generation ago just couldn't be built.
And that leaves us with a pretty cool question to think about. We've basically figured out how to program the most common building material on the planet, solid, dependable concrete, to act like a liquid. So the next time you see that gray sludge, don't just see sludge, see the science. And ask yourself, if we can do this now, what impossible things are we going to build next?